In this video, I will give you an introduction to projectile problems that include a significant interaction with the air. So what I have here is a diagram, a force diagram. I have chosen my coordinate system to have the origin at the center of where my object is. The positive x direction is to the right, the positive y points straight up. Now, this is my object, the projectile. And before I talk about the forces, I want to talk about the interactions. I have here the system schema. I have my object. It is interacting with the Earth with a gravitational interaction. This is what we typically see in introductory physics. Our projectiles have only one gravitational interaction, that's with the Earth. Now, in upper level classical mechanics courses, what we add is the interaction with the air, and in particular, this is a contact interaction with the air. You have to think, as the projectile is moving through the atmosphere, through the air, the air molecules around it will collide with the projectile as the projectile is moving through those molecules. So this is why it is a contact interaction. It is primarily the collisions between the molecules and the projectile, and that gives rise to the force. This here is the contact force from the air on the object, and also I have the gravitational force from the Earth on the object that points straight down. Now, what I have written here first is the gravitational force from the Earth on the object. This one will always point, assuming that the projectile does not travel much, this will always point in the negative y direction. So I have 0 in the x, minus mg in the y, and 0 in the z, or with different notation I can write minus mg y hat, and I can remind you with g I assume 9.8 meters per second squared. Now, the second force that I have to think about, this is the contact force from the air on the object. I will make the assumption here, okay, even though I will be adding some more to the model that we use in introductory physics, even though I'm adding to that, I'm not adding everything that we know about the contact interaction from the air to the projectile. I will make the assumption that I am dealing with a non-rotating object flying through the air. If you add rotation, if you have like a baseball, for example, if you add rotation to your object moving through the air, the interaction with the air becomes, you have to think about more terms. So, in one of the most simple cases of the object, the projectile flying through the air, I will say that this contact force from the air on the object is a function of the speed, and it points in the negative v hat direction, where v, I'm gonna make a note here, this v is the velocity of the object. So what this expression is telling me is that, I can write it again, the magnitude of that contact force with the air, the magnitude is shown by the value of this function for a particular speed, okay, which means it is the magnitude, the strength of this is changing as the speed of the projectile is changing, and the direction depends really on the direction of the velocity. So, if you're only interested in the magnitude of the interaction of the force with the air, you just need to calculate the value of this function if you want to find the magnitude. If you're interested in the direction, then this is what you need to look at, minus v hat. Now, if you want both, if you want the entire vector, then of course you have to take into account both of these terms. And I will add that the magnitude depends on the speed. As you can see, it's a variable, the speed of the projectile. Now, the magnitude of the contact force with the air actually is something that you will see in physics papers. You will often see the way that this can be derived. The experiment is done, and we keep track of the motion of the projectile, and we analyze it, let's say with video recording and software, and then we get the data and we do a fit, and we determine the function that best describes the experimental results. This is one way to get the function for a specific projectile, for a specific object. We do have a basic understanding of the physics of this, but this is a complicated, very complicated interaction. So don't be surprised if you see experiments on projectiles moving, and then the fit is done to the experimental results to determine the form of this function. Now, one simple way, one thing that I can say though, is that this function depends on the speed. You can say, well, let's say that it has two terms: a linear term that also depends on the speed, but in a linear fashion, plus a quadratic term that depends also on the speed, but in particular on speed squared. Now I will write those two. So b times the speed, this is the linear term, plus c times v squared, this is the quadratic term. So this corresponds to that, and the linear term corresponds to this one. Now, b and c themselves, I can say b depends on the diameter of the projectile, but also on the medium, on the nature of the medium, and c and this is by the way, in case, let me see if I can make it better. Okay, this is the Greek letter beta. There we go, this looks a little bit better. So b is the coefficient to the speed in the linear term, and c is the coefficient on the quadratic term. Both b and c depend on the diameter. So the d here, this is the diameter of the projectile, and veta, the coefficients veta and gamma, those depend on the nature of the medium. Like, is it air? Is it a different kind of medium where your object is moving? And I can make a note. So these two depend on the medium. Now you can see that c depends on the diameter of the object squared, whereas b has only linear dependence to the diameter of the object. So this is one way that we can use to model the magnitude of the contact force with the air. Okay, a sum of a linear and quadratic term. Now it often happens that from those two terms, only one of them is important. And what I mean important, if you make a theoretical prediction, let's say, and you find you only use the linear term. For example, I I completely disregard, neglect the quadratic term. I only include this in my theoretical calculations, and I make a prediction for how my object will move. If the linear term is indeed dominant, then my theoretical prediction will be very, very close to the experimental result if you perform the experiment. And in this case, to make we do that in physics, we take into account the dominant interaction. If the quadratic term is negligible, then get rid of it. Don't take it into account. If on the other hand you determine that it's the quadratic term that is dominant in the interaction with the air, then only include this one. Forget about the linear term in this function. Okay, you have to it is necessary to include the dominant interaction, the dominant parts of the interaction, and you have to neglect everything else so that you can have a simple model, as simple as possible, but at the same time with strong predictive power. You want your theoretical model to predict results similar to what you get in the experiment, but you don't want to have a very complicated model. You want to have a model as simple as possible. Now, how do you know which one of the two terms is dominant? If one of them, I forgot to mention, there is a case where the linear term will be dominant. There are cases where the quadratic term is dominant. There are cases where none of the two terms is dominant. Both of them are important, and in those cases you have to take them into account both. Okay, it would be wrong to only include one of them. Now, how do you know which one is more important than the other one, if any of them is more important? Well, you have to look at their size. So one thing that we can do is we can find the ratio of the two terms. And I can find the ratio. I can take the quadratic term and divide it with the linear term, and this will give me c times the speed squared divided by b divided by the speed, and the square with the speed cancels, so I have c over b times the speed, and then I know that c is gamma times the diameter squared, whereas I'm using this expression, b is vita times the diameter of the object, and then I have times the speed. I get rid of the square with a d, so I have gamma over vita times the diameter times the speed. Now, I mentioned before that the parameters, the coefficients gamma and vita, depend on the medium. If you have standard the state of standard temperature and pressure, I can give you the values for those. Vita is 1.6 times 10 to minus 4 with the units, whereas gamma this is in STP, and if you are in STP and you calculate this ratio, this will give you in STP, you will get that the ratio is and this is in with the units d times the speed. This is your ratio f quadratic over f linear. Both of them depend on speed. So if you want to determine if one of the two terms is dominant, then, and assuming that your situation is STP, then you can simply use this expression, or okay, so this is a more general one. Now this one is in STP. You can use the appropriate expression to determine what this ratio is. For example, let's say that you find that the ratio is like 100. What this practically means is that the quadratic term is 100 times greater than your linear term. In that case, I would get rid of the linear term when you do your theoretical calculations. Or imagine that you find that your ratio is 0.01, 1 over 100. What that's telling you is that the linear term is the one that is dominant in this case. Then there is no point in taking into account the quadratic term. So depending on what you find for the ratio of the two terms, then you can decide whether you're going to take one into account and which one, or both. So this is the process that you need to follow every time you have a problem that includes air resistance. You have to follow this process to see what makes more sense to do about the function that gives you the magnitude of that contact force with the air.